Hi everyone, in this video we'll be going over add last and size and we'll be talking about the empty SL list as well. Okay, so so far we've kind of been talking a lot about the SL list class as a whole at a high level, right? But we haven't really coded anything. So let's kind of start off this video by coding add last and size. And for coding add last, we'll move to the iPad. Hopefully you all will find this fun. Okay, so we have the SLList class before us, and it's very, very simple. So far, we have the private int node first here, and we have our constructor, okay? And what we want to do in this video is implement add last, okay? So before we start implementing add last, let's actually gain some intuition for how we can implement it, okay? So looking at this linked list provided, let's try to figure out what changes or what steps we can take to implement add last, okay? So let's say somebody calls add last of 4, okay? So what should happen here is we need to get somehow to the last link in the linked list. We somehow need to get here, and we need to change its dot rest to point to the link containing 4. That's the functionality we need to achieve, okay? In order to achieve that, we can't just like immediately get to this last link, right? That's like basically really, really hard because we don't have any reference to it. The only reference we have is a reference to this first link. So the idea here is we can have some pointer, let's call it P, initially pointing to that first link. Then we can use some sort of loop to keep moving P down until it makes it to the last link. Then once it's at the last link, what we can do is say p.rest is equal to the new int list, okay? So that's kind of the logic behind at last. So let's see it in action, okay? So the first thing that we wanted to do was have p point to first, okay? So we can say is int node p is equal to first. And the reason we can't just like move first down is that we'll lose the reference to the start. We have to create a new pointer. Then what we need to do is actually move P down to the end. So how do we know that P has made it to the last link? Well, the last link in the linked list has a dot rest that's null. So we want to keep moving P down while P dot rest is not equal to null. We will say P is equal to P dot rest. Okay, and after executing this code right here, we know that this is the current state of P. So all we have to do is say P dot rest is equal to a new int node consisting of 4 and null. Okay, so that's the implementation of add last. Let's hop back to the slides and we can take size from there. Okay, so in order to implement size, unfortunately, I went to an iPad demo, but I want y'all to stop the video here and try to think about to yourself, how can I implement size recursively? This is a really tough problem, so definitely stop and think about it for yourself. Okay, so kind of like, let's walk through the solution. What you all may have realized is that in order to implement size recursively, we need to keep track of the current int node that we're at, right? Every time I do a recursive call, I should keep updating the int node we are at, because we need to have some way of traversing this linked list. But the problem is that size doesn't have any instance attributes. So the only solution really to doing this recursively is creating another private helper function that we then call recursively, okay? And that's the solution here. The solution is that we'll create a private helper method, which we just named as size, because Java, you can have multiple methods of the same name as long as the arguments are different, the signature that is. So we have a method size that takes in an int node, and it allows us to keep traversing through this linked list by passing in the next int node each time. Okay, so that's the implementation of size. And the next question is, can we make this better? Is it possible? This is crazy, actually crazy idea here, ridiculous, that size is always constant time. Whenever I call the size method, it immediately gives me back a result. Is that possible? So yeah, pause the video again and try to think about how we could achieve something so crazy and cool, where size always takes us immediate time, okay? So the solution is that we can have a variable that caches the size of the list, okay? What that is doing is we're adding a size variable to the SLList class. And that size variable is just going to store the size of the SLList as it changes over time, right? And this is a crazy idea because now whenever we call size, I don't have to iterate through the entire SLList. I can just say, I have the size stored, here it is. Amazing, really, really cool. But one like small catch in computer science is that there's a saying, there ain't no such thing as a free lunch. So what this means, sometimes we have like a free lunch at a work event, but whenever you have a free lunch, there's always something that you're paying, right? That's like the idea. So in the size situation, we are doing the work of changing that size variable whenever we add or remove. So it is a lot of work that we do beforehand, but spreading the work over a ton of calls is better than doing it all in one call. So it is a net win regardless. Okay, so kind of looking back at that initial image, on the top we see we have the int list, that's the naked int list, and at the bottom we see we have our amazing SL list with the added size instance attribute. And what we can see is now the SLList class, it's still a middleman, but we can also store meta information about the entire list, like its size. And that's really, really cool going forward. Okay, so the next part of this video is we're going to try to figure out how we can represent the empty list without causing any problems. Okay, so what if we can represent the empty list just by setting first to null, right? Let's try that. So now, when we have an empty list, our first attribute is just set to null, right? As we can see with this constructor right here, that I can give you an empty SL list and the, the size is 0 and first is set to null, okay? But the problem with that, very slight problem, is that what we just coded up add last, right? And if we look at add last here, notice that when I do p.next is equal to, oh, just kidding. When I execute this call right here, notice that p is first, and if first is null, then p is null. And if I do null.next, it's going to throw a null pointer exception, okay? So this is the problem. So again, let's pause the video and try to think about how I could solve this problem. Right now, the add last, when first is null, is giving me a null pointer exception. So yeah, is there a solution here? So one possible solution is that we just add in an if statement, right? I say if first is null, then I execute this code, I solve that one condition, and then we keep going. But it seems a bit iffy. So in the next video, we'll explore a arguably better way of kind of counteracting this. So yeah, stay tuned.